In the year 2020, NASA is going to be sending the next rover to the planet Mars, and with this mission, they plan on demonstrating a new piece of technology that could revolutionize the way we explore these other planets. This isn't traveling faster or hopping over rocks, but rather the ability to take flight. So let's talk about that. So let's begin by discussing planetary exploration as a whole. Orbiters do a great job at being able to take images from space and getting a wide view of what the surface is actually like. Rovers do a great job at examining local areas, being able to take geological samples and see what the weather is like in that region. However, rovers can't really travel that far. Since there's so many scientific experiments on board, they usually have to travel really slow, which limit the distance they can travel altogether for the entire mission. Therefore, being able to fly across the surface and going much faster would enable you to go further distances and also help rovers see where they need to go and how they can maneuver the terrain more quickly. This leads us to the idea of being able to fly across the surface, like Mars or Venus. And in this case, the Mars Helicopter Scout is going to be a technological demonstrator to see how well this actually could perform in assistance to the Mars 2020 mission. Now later we'll get to the actual size of it, but it's very small in comparison to the actual rover. It's actually going to be attached underneath and not until a couple months after the rover lands on the surface when it will be deployed. Now, when I say technological demonstrator, that's NASA terms for we've never done it before, but we're going to see if it works. And they've actually claimed that it's a high risk, high reward, meaning that if the Mars Helicopter Scout fails, it's not going to be that big of a deal to the overall Mars 2020 rover mission. Whereas if it succeeds, it could be a really great reward and help in the navigation of the overall mission. So now that we know why a helicopter scout would be very helpful on Mars, let's discuss some of the technological challenges behind designing such a vehicle. First of all, and probably most obviously, the Martian atmosphere is only 1% of that here on Earth, which means if we wanted to fly a helicopter on Mars, that would be equivalent to flying a helicopter here on Earth at an altitude of 30,000 meters. Okay, so let's fly a helicopter at that altitude. However, the world record is only 13,000 meters. Meaning it's 17,000 meters below what we needed to do. Now before we touch base on how they overcome that problem, let's discuss something that's a little bit easier on Mars, and that's the gravitational force. Since Mars is smaller than Earth, it only has 38% of the gravitational force. Therefore, the blades only have to make up for about a third of the force they would need to on Earth. However, in terms of designing a vehicle, the atmosphere plays a much bigger challenge than the helpfulness of the gravity. So how exactly do they overcome that? Now, instead of just saying what NASA actually changed about the helicopter, let's step through scientifically taking the original problem and trying to propose a solution and see how well that actually relates to what NASA did. So first we need to understand something called dynamic pressure. And dynamic pressure is sort of like the amount of energy that you can get out of the air around you. Now, dynamic pressure is proportional to the density of the air that you're in times the velocity that you're traveling squared. Meaning if you're in a more dense atmosphere, you'll get more energy, or if you're traveling faster, you'll get more energy squared. So if we relate that dynamic pressure to our case, we really only have two things we can vary: the density of the atmosphere we're in and the velocity that the blades are traveling, or how fast they're rotating. And in this case, we can't control the density, but we do know that it's about 100 times smaller than what we're used to here on Earth. So we have to up the velocity, or we have to make the blades spin faster. But since it's a velocity squared component, we don't have to increase it by 100 times, but we only have to increase it by the square root of 100, or 10 times. So ultimately, if we wanted to take a helicopter on Earth and put it on Mars, we would say we need to spin the blades 10 times faster. And it turns out the average helicopter blade spins at around 300 revolutions per minute. Meaning if we wanted to put that on Mars, it would have to be 3,000 revolutions per minute, which sounds really high. But if we look at what NASA actually announced, they said that the Mars Helicopter Scout is going to be using 2,800 revolutions per minute. So we were just 200 revolutions per minute off by doing this really quick and easy calculation. So now that we were able to make that prediction and get fairly close to what NASA actually came up with, let's actually discuss the specifications of the helicopter. It has a mass of 1.8 kilograms. It has two rotor blades, both of which being 1.2 meters in diameter, and the chassis, or basically the payload of it, is only a 14 centimeter cube, so it's fairly small. However, the blades are pretty large compared to the chassis, and again, that's to make up for the low pressure on Mars. It has a flight time of 90 seconds, a maximum range of 600 meters, and a maximum altitude of 400 meters. It can travel in the horizontal direction at a maximum of 10 meters per second, and it can travel in the vertical direction at a maximum of 3 meters per second. Now, I did the math with all those numbers, and they don't really add up to the maximum range and the maximum vertical and horizontal velocity, but I'm trusting NASA on this one that they got that right. But wait a second, how is NASA going to control this thing if the flight time is only 90 seconds? Because it takes light longer than 90 seconds to get to Mars to be able to communicate. Well, it turns out it's going to be completely flown autonomously. It will have a pre-programmed control algorithm that's going to use its downward-facing camera to check the terrain, landing location, and its altitude. It'll also use an accelerometer to check how it's actually positioned, as well as its gyroscope. However, it's not going to be using a compass, which are usually used in control systems. But why no compass? Well, as you probably know, the magnetic field on Mars is incredibly weak, meaning a compass actually wouldn't really work. Therefore, it's thought that it might actually use one of its other cameras to be able to detect where the sun is in the sky to try and use that as another navigational feature. Now, the original plan for the Mars Helicopter Scout is just to go through a couple trial phases, see how well it can fly just up and down, maybe go a little bit of a distance away. But if it ends up being successful, this could help the rover in being able to navigate across the surface, like I mentioned before. The plan is for it to fly upwards of a couple hundred meters away to be able to find a trajectory or path that the rover can follow, and then if there's a point of interest, it might check it out ahead of time. Then it might either come back to the rover if there's no good path, or it will wait for the rover to meet up for it for its next flight. Mainly because the two can't be separated that far for communication issues. Now, another quick note is that the Mars Helicopter Scout is actually solar powered, meaning that it can recharge and refly about once per day. But it also means it's probably not going to last as long as the actual Mars 2020 rover, since it's being powered by an RTG and not relying on the sun. Now, the last thing I want to mention about the Mars Helicopter Scout is it doesn't really look like your typical helicopter, drone, or quadcopter that you see here on Earth. In a normal helicopter, you have a tail rotor, which is used to counteract the torque that's created by your main rotor. Now, there is a good way to think about this. If you've ever owned a cheap remote-controlled helicopter or seen a friend fly one, you'll probably notice that it spins out of control and crashes a lot of the time. And that is because you have to trim the tail rotor, because that's going to be counteracting the torque that your main rotor provides for lift. And this is due to something called the conservation of angular momentum. When you have the main rotor spinning, it creates lift, but it also creates a torque on the main vessel. To counteract that torque, you have another rotor farther back that is pushing in the horizontal direction, which stops it from spinning. So now that you know how a normal helicopter works, you may be asking, well, a quadcopter doesn't have that. It doesn't have something spinning in the horizontal direction. They're all facing upwards. And that's true. But the actual design of the blades on a quadcopter are flipped for two of them rather than the other two. They still provide lift upwards, however, since they're spinning in opposite directions, angular momentum is still conserved. Therefore, if you wanted to spin a quadcopter in air, all you'd have to do is slow down the two that are spinning in the same direction, which then means the only way for angular momentum to be conserved is to actually spin the entire vehicle. But the Mars Helicopter Scout doesn't use either of these techniques. It uses something a little bit from the helicopter and a little bit from the quadcopter. It uses a coaxial rotor, which means there are two blades spinning at the exact same rate, however in opposite directions. Now, the blades are flipped similar to that of the quadcopter, which allows both of the blades to create lift. However, it's similar to a helicopter because most of the lift comes from this one main axle. Now, you may ask, why aren't all helicopters or quadcopters like this? It seems pretty simple. However, a coaxial rotor design is very difficult to design from a mechanical standpoint, meaning if something was to go wrong or something was to break, the maintenance on it is very challenging. And in everyday helicopters or quadcopters, it's easier to perform maintenance on 4 separate rotors or 2 rotors that are spinning in the same direction than one rotor that is trying to spin spin in opposite directions on the same axle. But when we're sending it to something on Mars where maintenance isn't an option, then we don't have to worry about it. Therefore, to conserve angular momentum, mass, and design, all we have to do is use this coaxial rotor design. Now, if the Mars Helicopter Scout is successful, what other aerial missions would you like to see, whether going to Venus, Mars, or maybe even some of the upper atmospheres of the gas giants? Let me know in the comments below. But thank you for watching, and I hope to see you in the next one.